We are alone, and we may always be alone. I have spent my entire life searching for company in the cosmos. I have listened for signals from distant stars. I have sent messages into the void, golden records attached to spacecraft, carrying greetings in dozens of languages, music from every culture, images of our world and our species. I have stared at the night sky with a longing that borders on prayer, hoping that somewhere out there, someone is staring back. And I can tell you, with the full weight of that lifelong search, that we may never meet another intelligent species. Not because they don't exist, but because the universe is constructed in a way that keeps civilizations apart forever. Absolutely. By design, if design is even the right word for the cold mathematics of cosmic distances and cosmic time. This is the loneliest truth I know. Let me tell you why the dream of contact, the dream that has sustained humanity's imagination for centuries, may be nothing more than a dream. Let me explain why the silence of the cosmos is not mysterious but expected. And let me show you why, even if the galaxy teems with intelligent life, we may live and die without ever knowing it. The first thing you must understand is the scale of the problem, not the scale of the universe, though that is incomprehensibly vast, the scale of the improbability, the sheer mathematical impossibility of two civilizations existing at the same time, in the same place, with the ability and desire to communicate. The Milky Way galaxy contains approximately 200 billion stars. That number is so large that it loses all meaning. Let me try to make it concrete. If you counted one star per second, it would take you over 6,000 years to count them all. 6,000 years of continuous counting, without sleeping, without pausing, just pointing at stars and saying numbers. Many of those stars have planets. We now know this with certainty. The Kepler Space Telescope and its successors have revealed that planets are common, perhaps ubiquitous. On average, every star in the galaxy has at least one planet. Many have several. The galaxy contains hundreds of billions of worlds. Some of those worlds orbit in the habitable zones of their stars, where liquid water could exist on the surface. Estimates vary, but there may be tens of billions of potentially habitable planets in our galaxy alone. Tens of billions of places where life might arise. This sounds encouraging. Tens of billions of chances for life. Surely, among so many opportunities, intelligence must have evolved somewhere else. Surely, we are not alone. But now consider time. The Milky Way is approximately 13 billion years old. Stars have been forming, burning, and dying for most of that time. Planets have been coalescing, cooling, and developing for billions of years before Earth even existed. If intelligent life arises with any regularity, civilizations could have emerged billions of years ago. They could have risen and fallen 1,000 times before our sun ignited. Where are they? This is the question Enrico Fermi asked over lunch in 1950, and it has haunted us ever since. If the galaxy is old and vast, if planets are common and life is possible, why do we see no evidence of extraterrestrial intelligence? Where are the radio signals? Where are the spacecraft? Where are the megastructures that a billion-year-old civilization might have built? The silence is deafening, and it demands explanation. Some say the silence means we are alone. Perhaps life is rare. Perhaps intelligence is rarer still. Perhaps the evolution of technology is so improbable that it has happened only once, here, on this unremarkable planet, orbiting this unremarkable star, in this unremarkable corner of an unremarkable galaxy. I do not believe this. The chemistry of life is not exotic. The elements that compose our bodies, carbon, hydrogen, oxygen, nitrogen, are among the most common elements in the universe. The molecules of life, amino acids and sugars and nucleotides, form spontaneously in interstellar space. We have found them in meteorites, in comets, in the clouds of gas between stars. The ingredients for life are everywhere. And life on Earth arose quickly. The planet formed 4.5 billion years ago. Life appeared within the first billion years, possibly within the first few hundred million. This suggests that life is not a freak accident, but a natural consequence of chemistry given the right conditions. If life arose quickly here, it probably arose quickly on many other worlds as well. But life is not intelligence. Bacteria are alive but not intelligent. Plants are alive but not intelligent. For most of Earth's history, life was single-celled, simple, unthinking. Complex multicellular life appeared only about 600 million years ago. Intelligence, in the sense of tool use and abstract thought, appeared only in the last few million years. Technological civilization is only about 10,000 years old. Radio technology is barely a century old. The jump from life to intelligence is not automatic. It may not even be likely. Earth has hosted life for nearly 4 billion years, but intelligent, technological life has existed for an eye blink. If this ratio holds elsewhere, most planets with life would have no intelligent species. The galaxy might be full of bacteria and empty of minds. But let us assume that intelligence does arise elsewhere. Let us be generous and assume that it arises on 1 in a million habitable planets. That would still mean tens of thousands of intelligent species in the Milky Way. Tens of thousands of civilizations scattered across the galaxy, looking up at the same stars we see. Why haven't we heard from any of them? Here is where the mathematics become cruel. Space is vast. I have said this before, but I need to say it again because the vastness is the key to everything. The nearest star to our sun is Proxima Centauri, about 4.2 light years away. That sounds close by cosmic standards. It is not close by any standard that matters for contact. Light, the fastest thing in the universe, takes 4.2 years to travel from Proxima Centauri to Earth. A radio signal traveling at light speed would take the same time. If intelligent beings on a planet around Proxima Centauri sent us a message today, we would not receive it until 2029. Our reply would not reach them until 2033. A simple exchange of greetings would take over 8 years. And Proxima Centauri is close. Most stars in the galaxy are hundreds or thousands of light years away. A signal from the center of the galaxy would take 26,000 years to reach us. A signal from the far side of the galaxy would take 100,000 years. Communication across such distances is not a conversation, it is archaeology. But the problem is worse than mere distance. The problem is time. Civilizations have lifespans. They rise and fall. They flourish and collapse. Human technological civilization is about 10,000 years old, and we have nearly destroyed ourselves multiple times in just the last century. Nuclear weapons, climate change, engineered pandemics, artificial intelligence risks. The threats multiply faster than our wisdom to handle them. How long does a typical civilization last? We have only one data point, ourselves, and we are still here so far. But our track record is not encouraging. We have come close to extinction several times. We may yet succeed in destroying ourselves. Let us be optimistic and assume that the average technological civilization lasts 1 million years before it destroys itself, transforms into something unrecognizable, or simply loses interest in communication. 1 million years sounds like a long time. It is not long compared to the age of the galaxy. If civilizations arise randomly throughout the galaxy's history and last 1 million years each, the chance that any two civilizations exist at the same time is small, very small, cosmically small. The galaxy is 13 billion years old. 1 million years is less than 0.01% of that time. If a civilization arose around a star 5 billion years ago and lasted 1 million years, it has been dead for 4.999 billion years. Its signals passed through our solar system long before Earth formed. Its ruins have crumbled to dust. Its memory has been erased by the patient work of entropy. For two civilizations to communicate, they must not only exist in the same galaxy, they must exist at the same time. And the window of overlap may be vanishingly small. Imagine the history of the galaxy as a single calendar year. On this scale, 1 million years is about 40 minutes. The chance that two 40-minute windows overlap somewhere in that year is not zero. But the chance that they overlap while also being close enough in space to communicate is effectively zero. This is the temporal isolation problem. Even if the galaxy has hosted millions of civilizations throughout its history, they may never have overlapped in time. Each one may have risen and fallen alone, never knowing that others existed, never receiving a signal, never sending one that was received. We may be one of those civilizations. We may be shouting into a void that was full of voices a billion years ago and will be full of voices a billion years hence. But right now, at this moment in cosmic history, we may be the only ones speaking. The silence is not evidence that we are alone. It is evidence that the universe separates civilizations in time as effectively as it separates them in space. Let me tell you about the speed of light, because this cosmic speed limit is not merely an inconvenience. It is a prison that may keep every civilization in the universe locked in solitary confinement forever. Nothing travels faster than light. This is not a technological limitation that might be overcome with better engineering. It is a fundamental property of space-time itself, built into the structure of reality at the deepest level. Einstein showed us this over a century ago, and every experiment since has confirmed it. Light travels at approximately 299,792 kilometers per second. This sounds fast. In human terms, it is incomprehensibly fast. Light could circle the Earth 7.5 times in a single second. It could travel from Earth to the Moon in about 1.3 seconds. These are speeds beyond anything we experience in daily life. But the universe is built on a scale that dwarfs even light's speed. Light takes 4.2 years to reach the nearest star. It takes 100,000 years to cross our galaxy. It takes 2.5 million years to reach the nearest large galaxy, Andromeda. It takes billions of years to reach the most distant galaxies we can observe. At light speed, the fastest possible speed, crossing interstellar distances takes years. Crossing galactic distances takes millennia. Crossing intergalactic distances takes eons. And nothing travels at light speed except light itself. Any physical object, any spacecraft, any living being must travel slower, much slower. Our fastest spacecraft, the Parker Solar Probe, reaches speeds of about 700,000 kilometers per hour when it swings close to the Sunday. This is fast by human standards. It is pathetically slow by cosmic standards. At this speed, reaching the nearest star would take about 6,700 years. Reaching the center of the galaxy would take about 3.4 billion years. We could do better with advanced propulsion systems. Nuclear pulse propulsion might achieve 5 to 10% of light speed. Antimatter engines, if we could ever build them, might achieve 20 to 30% of light speed. But even at 30% of light speed, crossing the galaxy would take over 300,000 years. No civilization, no matter how advanced, can exceed the speed of light. This is not a matter of technology, it is a matter of physics. The equations of relativity show that as an object approaches light speed, the energy required to accelerate it further approaches infinity. You cannot reach light speed with finite energy. You certainly cannot exceed it. Some have proposed exotic workarounds, wormholes, tunnels through space-time that could connect distant points. Warp drives, distortions of space-time that could move a bubble of space faster than light while nothing inside the bubble exceeds local light speed. These are mathematically possible solutions to Einstein's equations. But mathematical possibility is not physical reality. We have no evidence that wormholes exist. Creating one would require exotic matter with negative energy density, matter that has never been observed and may not exist. Stabilizing one would require solving engineering problems that border on the impossible. Warp drives face similar obstacles. The Alcubierre drive, proposed in 1994, shows that a warp bubble is theoretically consistent with general relativity. But creating such a bubble would require more energy than exists in the observable universe, according to initial calculations. Later refinements reduce this requirement, but it remains astronomical. And even if you could create a warp bubble, there are unresolved questions about causality violations and quantum instabilities that might make the whole concept unworkable. I have spent decades thinking about these possibilities. I want them to be real. I want there to be a way around the cosmic speed limit, but wanting does not make it so. The physics, as we understand it, says no. And so we are left with the cold reality. Interstellar travel, if it is possible at all, takes decades at minimum, centuries more likely, millennia in many cases. No civilization can simply zip across the galaxy to visit another. The distances impose travel times that exceed individual lifespans, that may exceed the lifespans of civilizations themselves. Now consider what this means for contact between civilizations. Suppose an alien species exists around a star 1,000 light-years away. This is relatively close by galactic standards, well within the disk of the Milky Way, in our general neighborhood. If they sent a radio signal today, it would not reach us for 1,000 years. Our descendants, in the year 3025, might receive it. If they then sent a reply, it would not reach the aliens until the year 4025. A simple exchange of greetings would take 2,000 years. But would the alien civilization still exist in the year 4025? Would human civilization still exist? 2,000 years ago, the Roman Empire was near its peak. Every political structure, every language, every technology from that era has been transformed beyond recognition or has disappeared entirely. In 2,000 more years, what will remain of our civilization? Even if both civilizations endure, the exchange would be so slow as to be almost meaningless. You could not have a conversation. You could not exchange ideas in real time. You could only send monologues into the darkness and hope that someone would be listening when they arrived. This is communication across 1,000 light years. Now consider communication across 10,000 light years, across 50,000, across the full diameter of the galaxy. A signal from the far side of the Milky Way would take 100,000 years to reach us. Our reply would take another 100,000 years to reach them. The round-trip communication time would be 200,000 years. Human beings have existed as a species for about 300,000 years. Anatomically, modern humans have been around for perhaps 200,000 years. The entire history of our species is roughly the time it would take for one exchange of messages across the galaxy. No meaningful communication is possible on these timescales. By the time a reply arrives, the original senders may have evolved into something else entirely. Their civilization may have risen and fallen multiple times. Their planet may have been destroyed by its expanding sun. The very concept of communication may have become obsolete, replaced by something we cannot imagine. The speed of light is not just a speed limit, it is an isolation barrier. It keeps civilizations separate not just in space, but in time. It ensures that even if the galaxy is full of intelligent life, each intelligent species experiences itself as alone. Let me tell you about another problem that compounds the isolation, the problem of finding each other in the first place. The galaxy contains 200 billion stars. Space is three-dimensional. Stars are distributed throughout a disk, roughly 100,000 light-years in diameter and about 1,000 light-years thick. The volume is immense, approximately 8 trillion cubic light-years. If there are 10,000 technological civilizations in the galaxy right now, which is optimistic, the average distance between them would be about 50 light-years. That doesn't sound too bad. 50 light-years is a manageable distance, at least for radio communication. But finding those civilizations is another matter entirely. Radio signals spread out as they travel. A signal that is strong at its source becomes weak as it disperses across the vast distances of space. By the time it reaches 50 light-years away, it has spread over an enormous spherical surface. The energy per unit area is tiny, a whisper against the background noise of the cosmos. Our radio telescopes can detect only the most powerful signals from nearby stars. We could not detect our own radio leakage, the accidental emissions from our television broadcasts and radar systems, from even the nearest star. Those signals are too weak, too diffuse, too easily lost in the noise. To be detected across interstellar distances, a signal must be deliberately powerful. It must be aimed, it must be sustained. And it must be transmitted at a frequency and in a format that the receivers are looking for. This is the needle in the haystack problem, except the haystack is 100,000 light years across and the needle might not even be there. The SETI program, the Search for Extraterrestrial Intelligence, has been listening for signals since 1960. Over 60 years of searching, using increasingly sophisticated equipment, scanning millions of stars at millions of frequencies. The result, silence. Not a single confirmed signal from another civilization. This does not prove that no one is transmitting. It proves only that we haven't found them yet. The galaxy is vast. Our search has covered only a tiny fraction of it. The needle may be there, waiting to be discovered. But the silence should give us pause. If technological civilizations were common and long-lived, if they routinely built powerful transmitters and broadcast their presence to the cosmos, we might expect to have heard something by now. The fact that we haven't suggests that either civilizations are rare, or they are not broadcasting, or their broadcasts are in forms we don't recognize, or the distances are simply too great. Each of these possibilities points to the same conclusion: contact is hard, perhaps impossibly hard. Let me tell you about the direction problem, because even if civilizations are broadcasting, we might be looking in the wrong direction. The Milky Way is a disk, but it is not a flat disk. It has thickness, it has spiral arms, it has a central bulge and a halo of old stars and globular clusters. The distribution of stars is not uniform. When we search for signals, we must choose where to point our telescopes. We cannot look everywhere at once. We must make choices, prioritize some directions over others, hope that we guess correctly about where to look. If alien civilizations are concentrated in certain regions of the galaxy, regions we have not examined closely, we would miss them entirely. If they are broadcasting in directions that do not include us, their signals would never reach our telescopes, no matter how long we listened. The galaxy is not a small room where a shout can be heard in every corner. It is a vast wilderness where signals can pass within light years of each other and never intersect. Two civilizations could exist simultaneously, both broadcasting, both listening, and never detect each other because their signals pass like ships in the night. This geometric improbability adds another layer to our isolation. It is not enough for civilizations to exist at the same time. They must also be looking in the right direction, transmitting at the right frequency, using the right encoding, with enough power to be detectable at the distances involved. The probability that all of these factors align is small, perhaps vanishingly small. Now, let me tell you about something that makes the problem even worse: the problem of recognition. Suppose an alien signal reached Earth today. Would we recognize it as artificial? We assume that alien signals would be obviously different from natural phenomena. They would be narrowband, concentrated at a single frequency, unlike the broadband noise of natural radio sources. They would be modulated, carrying information in patterns that could not arise by chance. They would stand out against the background of cosmic static, like a lighthouse in the darkness. But this assumption may be wrong. Our ideas about what artificial signals look like are based on our own technology, our own communication methods, our own assumptions about how intelligent beings would choose to transmit. Alien civilizations might use completely different methods that we would not recognize as artificial. They might communicate using neutrinos instead of radio waves. Neutrinos pass through matter almost without interaction, making them difficult to detect but also difficult to block. A neutrino-based communication system would be invisible to our radio telescopes. They might communicate using gravitational waves. These ripples in space-time were only detected for the first time in 2015. We are just beginning to develop gravitational wave astronomy. An alien civilization might have been broadcasting gravitational messages for millennia that we lacked the technology to detect. They might communicate using methods we cannot even imagine. Our technology is a century old. Theirs might be 1,000,000 years old or 1,000,000,000. The gap between our capabilities and theirs might be greater than the gap between our capabilities and those of bacteria. We might be surrounded by alien signals that we lack the conceptual framework to perceive. This is the recognition problem. Even if signals are reaching Earth right now, we might not know it. We might be filtering them out as noise. We might be looking right at them and seeing nothing because we don't know what to look for. The universe might be full of voices, and we might be deaf to all of them. Let me tell you about something that haunts every serious thinker about extraterrestrial intelligence. The question of why they would want to contact us at all. We assume that alien civilizations would be interested in communication. We assume they would want to find us, talk to us, share knowledge with us. This assumption is so deep in our thinking that we rarely question it, but it may be entirely wrong. Consider the asymmetry of any contact between civilizations. If an alien civilization is capable of detecting us, capable of sending signals across interstellar distances, capable of the kind of technological feats that interstellar communication requires, they are almost certainly far more advanced than we are. The odds that two civilizations would be at exactly the same level of development are essentially zero. Technological civilization on Earth is about 10,000 years old. Radio technology is about a century old. In cosmic terms, we are newborns, barely hatched, still learning to crawl. An alien civilization might be 1,000 years ahead of us, or 1,000,000 years, or 1,000,000,000. The difference between us and a civilization 1,000,000 years more advanced than us is greater than the difference between us and bacteria. We share more in common, technologically and cognitively, with single-celled organisms than we would with beings who have had 1,000,000 additional years to develop. What would such beings want from us? We imagine that advanced civilizations would be curious about other life forms. We imagine they would want to collect information, to catalog the species of the galaxy, to understand the diversity of intelligence. This is projection. We are curious. We study less advanced species. We assume aliens would do the same. But our curiosity about other species is limited. We study bacteria when they are useful or dangerous to us. We study animals when they provide insight into biology or when they entertain us. But we do not attempt to communicate with them as equals. We do not send radio messages to ant colonies or try to establish diplomatic relations with dolphins. To a civilization 1,000,000 years more advanced than us, we might be as ants. Interesting, perhaps. Worthy of study, maybe, but not worthy of communication. Not capable of communication in any meaningful sense. The cognitive gap would be too vast. And this assumes they would notice us at all. A civilization sufficiently advanced might have moved beyond the concerns that occupy us. They might have transcended biology, uploaded their consciousness into artificial substrates, merged into a collective intelligence, or evolved into forms of existence we cannot comprehend. Our radio signals, our small planet, our brief technological adolescence might be beneath their notice entirely. Some have suggested that advanced civilizations would be altruistic. They would want to help younger species, guide them, share the accumulated wisdom of galactic history. This is a comforting thought. It is also entirely speculative. We have no reason to believe that intelligence implies benevolence. Our own history suggests the opposite. When technologically advanced human civilizations have encountered less advanced ones, the results have generally been catastrophic for the less advanced. Conquest, exploitation, disease, cultural annihilation. The pattern repeats throughout human history. Would alien civilizations be different? Perhaps. They might have evolved past the tribal instincts that make us suspicious of strangers. They might have developed ethical frameworks that extend moral consideration to all intelligent beings. They might be benevolent in ways we cannot imagine. Or they might not. They might be indifferent, they might be hostile, they might view us as resources to be exploited, or threats to be eliminated, or curiosities to be collected. We have no way of knowing. This uncertainty argues for caution. Some scientists, including Stephen Hawking, have warned against actively broadcasting our presence to the cosmos. We do not know who might be listening. We do not know how they might respond. Announcing our existence to the universe might be the most dangerous thing our species has ever done. Others argue that it is too late for caution. Our radio signals have been leaking into space for a century. Any civilization within 100 light years that has radio telescopes pointed in our direction already knows we are here. The cat is out of the bag. But intentional broadcasts are different from accidental leakage. Our television signals are weak, diffuse, hard to detect at interstellar distances. A powerful, focused beacon would be another matter. It would announce not just our existence, but our desire for contact, our willingness to engage, perhaps our vulnerability. I am not suggesting that we hide in fear. I am suggesting that the assumption of benevolent contact is unwarranted. The universe owes us nothing. Other civilizations owe us nothing. If we ever do make contact, we should be prepared for any response, including no response at all. Let me tell you about the zoo hypothesis, because it offers one explanation for the silence that is both comforting and disturbing. Perhaps advanced civilizations know we are here. Perhaps they have been watching us for millennia, monitoring our development, observing our behavior. Perhaps they have chosen not to contact us, not because they cannot, but because they have decided not to. The zoo hypothesis suggests that Earth is a nature preserve, a protected area where a primitive species is allowed to develop without outside interference. The advanced civilizations of the galaxy have agreed, perhaps through some kind of galactic protocol, to leave us alone until we reach a certain level of development. This would explain the silence. The aliens are there, but they are deliberately not communicating. They are watching and waiting. There is something appealing about this idea. It suggests that we are not alone, that the galaxy is populated with wise and patient beings who care about our development. It suggests that the silence is temporary, that someday we will graduate from the zoo and join the galactic community. But the zoo hypothesis is also disturbing. It implies that we are being watched without our knowledge or consent. It implies that our history, our struggles, our achievements and failures are entertainment or education for beings we have never met. It implies a paternalism that many would find offensive, a judgment that we are not yet ready for contact, that we are not yet mature enough to handle the truth. And there is a deeper problem with the zoo hypothesis. It requires coordination among all advanced civilizations in the galaxy. Every single civilization must agree to the non-interference policy. Every single one must enforce it. If even one civilization decided to break the silence, the policy would fail. The probability that all civilizations would agree on such a policy and that none would ever defect seems low. Civilizations would have different values, different priorities, different ideas about how to treat younger species. Expecting unanimity across millions of worlds over millions of years strains credulity. The zoo hypothesis is possible, but it requires assumptions about galactic sociology that we have no way to verify. It is a comforting story, but it may be nothing more than a story. Let me tell you about another possibility that is less comforting. The Great Filter, the Fermi paradox, asks why we don't see evidence of alien civilizations. One answer is that something prevents civilizations from becoming visible on a galactic scale. Something stops them, destroys them, or transforms them before they can spread across the stars. This something is called the Great Filter. It is a barrier, somewhere in the development from dead matter to galaxy-spanning civilization, that almost no species passes through. The filter might be behind us. Perhaps the origin of life is extraordinarily improbable. Perhaps the evolution of complex cells, or multicellular organisms, or intelligence, or technology is so unlikely that it almost never happens. If this is true, we are rare. We have passed through the filter. The galaxy is empty because we are among the first to make it this far. Or the filter might be ahead of us. Perhaps civilizations routinely destroy themselves shortly after developing advanced technology. Nuclear war, engineered pandemics, artificial intelligence gone wrong, climate catastrophe, environmental collapse. Perhaps every species that develops the power to destroy itself does so, inevitably, before it can spread beyond its home world. If the filter is ahead of us, we are doomed, not doomed to loneliness, but doomed to extinction. The silence of the cosmos is the silence of graveyards, of civilizations that rose and fell and left no trace, of species that burned bright for a moment and then vanished forever. We do not know where the filter is. We do not know if we have passed it or if it awaits us. But the silence suggests that something, somewhere, prevents civilizations from filling the galaxy. Either they don't arise or they don't last. This is perhaps the most disturbing implication of the Fermi paradox. The silence is not neutral, it is evidence. Evidence that something is wrong. Either intelligent life is rare, or it is fragile, or it is self-destructive. None of these possibilities is comforting. Let me tell you about the timing problem in more detail, because it may be the simplest explanation for our solitude. The universe is 13.8 billion years old. The first stars formed about 13.5 billion years ago. But these early stars were not like our Sunday. They were massive, hot, and short-lived. They burned through their fuel in millions of years and exploded as supernovae. These explosions created the heavy elements, the carbon and oxygen and iron that life requires, but they also sterilized their surroundings with radiation. The first generation of stars had to live and die before planets like Earth could form. The heavy elements had to accumulate in the interstellar medium. Second and third generation stars had to form from this enriched material. This took time, billions of years. Stars like our Sun, with planetary systems capable of hosting life, probably did not become common until about 10 billion years ago. Earth formed 4.5 billion years ago, roughly in the middle of this period. Life arose quickly, but complex life took billions of years to develop. Intelligent life appeared only in the last few million years. What if this timeline is typical? What if complex life requires billions of years of stable conditions to evolve? What if intelligent life tends to appear only after a planet has had time to develop a rich biosphere? If this is the case, most intelligent civilizations in the galaxy might be arising right now, give or take a few 100 million years. The universe might be entering a period when intelligence becomes common after billions of years when it was rare or absent. We might be among the first, not the only civilization in the galaxy, but among the earliest wave of civilizations to achieve technology. The Great Silence might not indicate that civilizations are rare or self-destructive. It might indicate that we are early, that we have arrived at the party before the other guests. This is speculative, but it is consistent with what we know about cosmic history. The conditions for life have not always existed. They emerged gradually over billions of years. We may be witnesses to the dawn of intelligence in the galaxy, not latecomers to an ancient civilization that has already risen and fallen. If this is true, the silence makes sense. There is no one to hear because there is no one yet to speak. The galaxy is a nursery, and we are among the first infants to open our eyes. But this offers cold comfort. Being first is a kind of loneliness too. The other civilizations that may arise in the future are no more accessible to us than the civilizations that might have existed in the past. We cannot wait for them. We cannot communicate with beings who will not exist for millions of years. We are alone in time, whether that time is past or future. Let me tell you about what contact would actually require, because the practical obstacles are as daunting as the theoretical ones. Suppose against all odds that an alien civilization exists right now, within communication range, broadcasting signals that we could detect. Suppose they want to be found. Suppose they are actively trying to make contact. What would it take for that contact to actually happen? First, we would need to be listening at the right time. Radio signals travel at the speed of light, but they do not last forever. A signal that passes Earth while our telescopes are pointed elsewhere is lost. We cannot rewind the cosmic broadcast. We cannot ask for a repeat. If we miss it, it is gone. The SETI program has operated for over 60 years, but it has not listened continuously. Funding has been sporadic. Telescope time is limited. We have sampled the sky, not surveyed it. The coverage is incomplete, full of gaps in time and space and frequency. An alien civilization might have sent a signal toward Earth 1,000 years ago. It would have passed through our solar system while our ancestors were building cathedrals and fighting crusades. No one was listening. The signal continued on into space, carrying its message to no one. Or they might send a signal tomorrow aimed at a star they observed a century ago when Earth's radio emissions first reached them. By the time the signal arrives, we might have abandoned radio astronomy. We might have destroyed ourselves. We might have evolved beyond recognition. The signal would arrive at a planet that could not receive it. The timing must be precise, not just within millions of years, but within the window when both civilizations are capable of and interested in communication. That window might be centuries, it might be decades. In cosmic terms, it is nothing. Second, we would need to be listening at the right frequency. The electromagnetic spectrum is vast, spanning from radio waves with wavelengths of kilometers to gamma rays with wavelengths smaller than atoms. An alien signal could be transmitted at any frequency within this enormous range. We have guesses about which frequencies might be preferred. The hydrogen line at 1,420 megahertz is a natural choice, a frequency associated with the most common element in the universe. The water hole, the quiet region between the hydrogen line and the hydroxyl line, has been suggested as a natural meeting place for interstellar communication. These are reasonable guesses based on physics and logic. But aliens might not share our logic. They might transmit at frequencies we have not considered, using reasoning we cannot follow. They might use spread spectrum techniques that smear the signal across many frequencies, making it harder to detect but more resistant to interference. They might use communication methods that are not electromagnetic at all. We cannot listen to every frequency simultaneously. Our receivers have limited bandwidth. We must choose where to focus, and every choice excludes alternatives. The signal might be there at a frequency we are not monitoring, waiting to be discovered by someone who thinks to look. Third, we would need to recognize the signal as artificial. I have discussed this problem before, but let me elaborate on just how difficult recognition might be. Natural phenomena produce radio signals. Pulsars emit regular pulses. Quasars produce enormous radio emissions. Magnetars, fast radio bursts, cosmic microwave background radiation, the universe is noisy. Against this background of natural static, we must identify signals that are clearly artificial. We assume artificial signals would have characteristics that natural sources lack: narrow bandwidth, regular patterns, mathematical content, information that could not arise by chance. These are reasonable assumptions, but they are assumptions nonetheless. The first pulsar, discovered in 1967, was initially nicknamed LGM-1 for little green men. Its regular pulses seemed so artificial that the discoverers briefly considered the possibility that they had detected an alien beacon. They hadn't. Pulsars are natural objects, rotating neutron stars that sweep beams of radio waves across the sky like cosmic lighthouses. Nature can produce patterns that seem artificial. Conversely, artificial signals might seem natural. A civilization that wanted to hide might disguise its transmissions as natural phenomena. A civilization using very different technology might produce signals that look like noise to us. The boundary between natural and artificial might be blurrier than we assume. Even if we detected a clearly artificial signal, we would face the problem of interpretation. The signal would presumably carry information, but in what format? Using what encoding? Conveying what concepts? Human languages are difficult enough to translate. We have spent centuries deciphering ancient scripts, and some remain undecoded. These were human languages, produced by human minds, expressing human concepts. An alien language would be produced by alien minds, expressing alien concepts. The cognitive gap might be unbridgeable. Mathematics is sometimes proposed as a universal language. Certainly, mathematical truths are universal. 2 + 2 = 4 everywhere in the cosmos. The ratio of a circle's circumference to its diameter is pi, regardless of who measures it. These truths could serve as a starting point for communication. But mathematics alone cannot convey meaning. It cannot express emotions, describe experiences, explain cultures, or share stories. A message consisting entirely of mathematical proofs would demonstrate intelligence, but would tell us almost nothing about the beings who sent it. We would know they could count. we would not know who they are. Any meaningful communication requires shared context. When humans communicate, we draw on millennia of shared history, shared biology, shared experience. We understand each other because we are fundamentally similar, because our brains evolved under the same conditions, because we face the same challenges of survival and reproduction. Aliens would share none of this context. Their biology would be different. Their history would be different. Their psychology, if they have anything resembling psychology, would be different. The concepts that seem obvious to us might be incomprehensible to them, and vice versa. Translation might not just be difficult, it might be impossible. Let me tell you about the distances involved in physical contact, because communication is only part of the challenge. Suppose we received a signal. Suppose we decoded it. Suppose it contained an invitation, coordinates for a meeting place, instructions for how to reach them. Could we go? The nearest stars are light years away. At our current technological level, reaching even the nearest star would take tens of thousands of years. At the most optimistic projections of future technology, it might take decades to centuries. A species that invited us to visit would need to wait for our arrival. If they are 1,000 light years away, our fastest conceivable spacecraft would take tens of thousands of years to reach them. By the time we arrived, their civilization might have evolved beyond recognition, collapsed entirely, or lost interest in the invitation they sent millennia ago. And we would face the same problem in reverse. If we invited aliens to visit us, we would need to maintain our civilization, our interest, and our welcoming posture for however long it took them to arrive. That might be centuries. That might be millennia. Human civilizations do not typically last that long in stable form. Physical contact between civilizations requires either travel times that exceed the lifespans of civilizations or technologies that violate known physics. Neither option is promising. Some have proposed generation ships, spacecraft that travel for centuries with crews that reproduce along the way. The original crew would die en route, but their descendants would eventually arrive. This is theoretically possible, but it requires solving every problem of long duration, space flight, life support, social stability, genetic diversity, and more, and it requires a civilization willing to invest enormous resources in a project whose benefits would accrue only to people not yet born. Others have proposed suspended animation, freezing travelers for the journey and reviving them at the destination. This remains science fiction. We cannot currently freeze and revive human beings without killing them. The ice crystals that form in freezing tissue destroy cellular structures. Even if we solve this problem, we would still face journey times of centuries or millennia. The physics is clear. Physical contact between civilizations in different star systems is, if not impossible, so difficult as to be effectively impossible with any technology we can currently imagine or plausibly project. This leaves us with communication as the only realistic form of contact. Electromagnetic signals traveling at the speed of light, carrying information across the void. Not a handshake, not a meeting, not an exchange of ambassadors, just messages, just words in the darkness. And even this limited form of contact faces all the obstacles I have described. The timing problem, the distance problem, the recognition problem, the translation problem. Each obstacle alone might be surmountable. Together, they form a barrier that may be insurmountable. Let me tell you about something called the Fermi estimation, because it helps quantify just how unlikely contact might be. In 1961, astronomer Frank Drake developed an equation to estimate the number of communicating civilizations in the galaxy. The Drake equation multiplies together various factors: the rate of star formation, the fraction of stars with planets, the fraction of planets that could support life, the fraction where life actually develops, the fraction where intelligence evolves, the fraction that develops technology, and the average lifetime of technological civilizations. Each factor is uncertain. Some are very uncertain. The equation is not a calculation so much as a framework for thinking about the problem, a way of organizing our ignorance. Optimists plug in favorable numbers and conclude that millions of civilizations might exist in the galaxy right now, Pessimists plug in unfavorable numbers and conclude that we are probably alone. The honest answer is that we don't know. We have one data point, Earth, and one data point does not constrain an equation with 7 variables. The range of possible answers spans from 0 to billions. But even if we accept optimistic estimates, contact remains unlikely. 1 million civilizations in a galaxy of 200 billion stars means one civilization per 200,000 stars. The nearest one might be hundreds of light years away. Communication would take centuries. Physical contact would take millennia. And 1 million civilizations scattered across the galaxy, each lasting perhaps 1 million years, would still represent only a tiny fraction of the galaxy's history. The timing problem remains. The distance problem remains. The recognition problem remains. The Drake equation does not give us hope. It gives us a framework for understanding why hope may be misplaced. Now let me tell you why. Despite everything I have said, the search for extraterrestrial intelligence remains one of the most important endeavors our species has ever undertaken. And let me tell you why the answer, whether we find it or not, matters profoundly for our understanding of ourselves. I have spent this entire discussion explaining why we may never meet aliens. The distances are too vast. The timescales are too long. The windows of overlap are too narrow. The methods of communication are too uncertain. The chances of recognition are too slim. Every factor works against us. The universe seems designed, if design is the right word, to keep civilizations apart. And yet, I believe we must keep searching. Not because I am optimistic about success, I am not. The arguments I have presented are strong, and I believe them. The probability that we will detect an alien signal in my lifetime, or in the lifetime of anyone now living, may be vanishingly small. The probability that we will ever make physical contact with another intelligent species may be effectively 0. But probability is not certainty. We do not know that we are alone. We suspect it, we have reasons to believe it, but we have not proven it. And until we have proven it, the search continues to make sense. Here is why. The question of whether we are alone in the universe is one of the most profound questions humanity has ever asked. It touches on philosophy, theology, biology, physics, and the deepest mysteries of existence. Are we unique? Are we typical? Is consciousness a cosmic accident or a cosmic imperative? Does life inevitably lead to intelligence, or are we a freak occurrence in a dead universe? We cannot answer these questions from our armchairs. We cannot deduce the existence or non-existence of alien life from first principles. We must look. We must listen. We must search the cosmos with every tool at our disposal and see what we find. The search itself has value, regardless of its outcome. If we search and find nothing, that tells us something profound about our place in the universe. It suggests that we are rare, perhaps unique, perhaps the only minds in an incomprehensibly vast cosmos. This would be a staggering realization, both humbling and elevating. We would be alone, but we would know that we are alone. That knowledge, however lonely, would be valuable. If we search and find something, anything, even a single signal from a single civilization, that would transform our understanding of existence. It would prove that intelligence is not confined to Earth, that the universe produces minds, that consciousness is not a fluke, but a feature of cosmic evolution. Even if we could never communicate meaningfully, even if the distance remained forever unbridgeable, we would know that we have company. We would know that we are not alone. Either answer matters. Either answer changes everything. Let me tell you about what the search has already taught us, because the benefits extend far beyond the question of alien life. The technologies developed for SETI have applications throughout astronomy. The signal processing techniques, the antenna designs, the data analysis methods, all of these have contributed to our understanding of the cosmos. SETI researchers have discovered pulsars, studied quasars, mapped the distribution of hydrogen in the galaxy. The search for alien intelligence has advanced the search for cosmic understanding. More broadly, SETI has forced us to think carefully about the nature of intelligence, communication, and civilization. What would an alien civilization look like? How would it communicate? What would it value? These questions have no easy answers, but asking them has deepened our understanding of ourselves. We learn about humanity by imagining what non-humanity might be like. The search has also fostered international cooperation. SETI is a global endeavor, transcending national boundaries and political conflicts. Scientists from many countries work together, sharing data, coordinating observations, pursuing a common goal. In a world often divided by tribal loyalties, the search for extraterrestrial intelligence reminds us that we are all inhabitants of the same small planet, all members of the same species, all facing the same cosmic questions. Let me tell you about the value of the search, even if we never succeed. Some have argued that SETI is a waste of resources. If the probability of success is low, why bother? Why not spend the money on more productive research, on problems we can actually solve? This argument misunderstands the nature of scientific inquiry. We do not know in advance which questions will yield answers. We cannot predict which searches will succeed. The history of science is full of discoveries that came from unexpected directions, from researchers pursuing questions that seemed impractical or unlikely to succeed. Moreover, the resources devoted to SETI are modest. The entire history of the search has cost less than a single Hollywood movie. The ongoing efforts are funded largely by private donations, not government budgets. The opportunity cost is minimal. We are not choosing between SETI and curing cancer. We are choosing between SETI and nothing. And there is something to be said for pursuing questions that matter, even if the answers are uncertain. The search for extraterrestrial intelligence is not practical in the narrow sense. It will not cure diseases or generate profits or solve immediate problems, but it addresses a question that humans have asked since they first looked up at the stars. Are we alone? That question deserves an answer, or at least it deserves an honest attempt at an answer. Let me tell you about the long view, because the search for extraterrestrial intelligence is not a project for a single generation. We have been searching for 60 years. We have found nothing. Should we give up? No. 60 years is nothing on cosmic timescales. It is nothing on the timescales relevant to interstellar communication. A signal sent from a star 1,000 light years away would have been traveling since the time of the Norman conquest. Our 60 years of listening is an eye blink, a moment of attention in a conversation that might span millennia. The search must be sustained across generations. It must be institutionalized, funded, maintained, even when it produces no results. We must listen not for years or decades, but for centuries. We must accept that those who begin the search may not live to see its conclusion. We must pass the torch to our descendants and trust them to continue. This is difficult. Humans are not patient. We want results now. We want to see the fruits of our labor within our lifetimes. A project that spans centuries goes against our nature. But some projects require centuries. Cathedrals took centuries to build. The scientific enterprise itself has been building for centuries and will continue for centuries more. The search for extraterrestrial intelligence is a cathedral of the mind, a project that transcends individual lives, a gift to the future from the present. Even if we never succeed, the search will have been worthwhile. It will have represented humanity at its best, asking the biggest questions, pursuing the deepest mysteries, refusing to accept ignorance as inevitable. It will have shown that we are a species capable of looking beyond our immediate needs, beyond our tribal conflicts, beyond our small planet, toward the vast cosmos that surrounds us. Let me tell you what I hope for, because hope is not the same as expectation. I hope that we are not alone. I hope that somewhere in this vast universe, other minds are looking up at the stars, wondering the same things we wonder, asking the same questions we ask. I hope that intelligence is common, that consciousness is a cosmic phenomenon, that the universe is full of beings capable of thought and feeling and wonder. I hope that someday, somehow, we will make contact. Maybe not in my lifetime, maybe not for centuries, but someday, a signal received, a message decoded, the knowledge that we have company in the cosmos. This hope may be unfounded. The universe may be empty. We may be the only minds in an incomprehensibly vast darkness. The silence may be permanent. But I refuse to stop hoping. I refuse to accept loneliness as our inevitable fate. I refuse to stop searching, stop listening, stop looking up at the stars with the ancient question on my lips. Is anyone there? The search for extraterrestrial intelligence is an act of faith, not religious faith, but something like it. Faith that the universe is comprehensible, faith that questions have answers, faith that the search itself has meaning, regardless of what we find. We may be alone. We may always be alone. The distances may be too vast, the time scales too long, the obstacles too many. Everything I have told you tonight suggests that contact with alien intelligence may be impossible. But impossibility has been proclaimed before. Flight was impossible until it wasn't. Space travel was impossible until it wasn't. Every expansion of human capability has been preceded by confident declarations that it could not be done. I am not predicting that we will find aliens. I am saying that we do not know. We cannot know without searching, and the search, whatever its outcome, ennobles us. It makes us larger than our immediate concerns. It connects us to the cosmos and to the future. When I look up at the night sky, I see countless stars, each one a sun, many with planets, some perhaps with life. I do not know if any of those worlds hold minds like ours. I do not know if anyone is looking back at me across the light years. I may never know, but I will keep looking. We will keep looking. Humanity will keep looking for as long as we exist, because that is who we are. We are the species that asks questions. We are the species that searches. We are the species that refuses to accept mystery as the final answer. The cosmos is vast and old and silent. We are small and young and full of questions. The disparity is absurd. A species that has existed for an eye blink on a planet that is a mote of dust, daring to ask whether anyone else exists in a universe of trillions of galaxies. But we ask anyway, we search anyway, we hope anyway. Because that is what it means to be human. We reach for things beyond our grasp. We ask questions that may have no answers. We send messages into the void, not knowing if anyone will ever hear them, because the sending itself matters, because the reaching itself is noble, because the hope itself is precious. We may never meet aliens. The universe may keep us forever alone. But the search will continue, generation after generation, century after century, for as long as there are humans to look up at the stars and wonder. And if someday, against all odds, we do receive a signal, if we do find proof that we are not alone, that moment will be worth all the centuries of silence that preceded it. It will be worth all the searching. It will be the most important discovery in human history. Until then, we wait, we watch, we listen. The universe is silent, but we are not.